Rise here, and today is our second episode of our series Contour Integral in Physics, where I illustrate how similarly abstract concepts in complex analysis can actually appear in physics applications. And today we are talking about the retarded propagator in electrodynamics. It is worth noting that the propagator involves doing this integral that does not give a meaningful value, and so we push the poles of this integral slightly up or slightly down, and there are 4 different ways to do it, and that will result in 4 different propagators, namely the retarded propagator, the advanced propagator, and 2 Feynman propagators. So in this video we're going to talk about the retarded propagator in electrodynamics because that makes the most physical sense, but do note that the Feynman propagator actually appears in quantum field theory because of its ability to time order. So yeah, hopefully I'll be able to cover that soon, but in this video we are just focusing on the retarded propagator. So what is this thing? So in electrodynamics, let's start off in electrodynamics first. We have Maxwell's equations, of course, and if we reformulate it in the potential formalism, namely instead of having E and B in the usual Maxwell's equations, we formulate it in terms of phi and A, where A is the where phi is the scalar potential and A is the vector potential. So if we formulate it in such, we obtain the following 2 equations, the 2 Maxwell's equations in potential formalism, and then because there's a gauge degree of freedom for our potentials, we can choose the Lorentz gauge, and this will simplify the 2 Maxwell's equations into the following 2 equations. Now we see that they're almost identical in that they both deal with this differential operator. So we want to find the Green's functions with this differential operator, and the Green functions would be able to we are able to integrate over the Green's function and use it to find the general solution to these 2 equations. So in order to solve these 2 equations, which is the electromagnetism in the Lorentz gauge, we need to find the Green's functions to this differential operator. This Green's function will act as this Green function is sort of like an inverse of this differential operator, in the sense of inverse in linear algebra. So we need to solve this differential equation. This differential equation is now our goal, and to do so we use Fourier series, and we compute the right hand side and the left hand side, and we obtain, which I'll not show the details in this video, but we obtain the following expression for the Green's function. This Green function might also be known as the propagator, and namely, what do we observe? We need to evaluate this particular integral, right? And this is just a constant term, so it pulls out of this integral, this d omega integral. So with that done, our mathematical problem now reduces to finding this integral. Now how do we do this integral? We see that we integrate along the real axis, but there are 2 poles, minus ck and ck. So at these 2 poles, the integral breaks down. So we are unable to assign a meaningful value, or rather we are unable to assign a direct value to this integral. However, we can assign a meaningful value to a very similar integral, and that is the integral where you do the following path, where you integrate along the following path. We bring it out into the complex plane in a small semicircle around the pole in a very small radius, and this integral from minus infinity to infinity, where you hop over the poles, is known as the retarded propagator. So now it can be shown that instead of evaluating this integral along this this contour that jumps over it, you can just evaluate the integral over the real axis, where you push down the poles to minus ck minus I epsilon and ck minus I epsilon. So now we just need to evaluate the so by making a choice of a contour, we are saying we are assigning a meaningful value to this integral, and the choice of the contour we choose is the retarded contour. So we choose this contour, and essentially our whole problem reduces to calculating this particular contour integral, or this particular integral from minus infinity to infinity of this integrand. Now I will refer, throughout this video, I'll refer to this part as f of omega for brevity. And what I'll show in this video is how this integral evaluates to the following value. So if t is less than t prime, this integral evaluates to 0, and if t is greater than t prime, then it evaluates to this value. So how do we do that? So let's do the first case. So if t is less than t prime, then the first thing we know is that minus t prime is greater than 0. Then we can consider the contour, the upper plane contour. So we have this line that we're integrating over, and let's close the contour up with this upper semicircle. So I'll call the semicircle S, and I'll call the line I'll denote it with minus infinity to plus infinity. So what happens then? Our contour integral over the entire contour C is simply equals to the straight line integral plus the semicircle integral. However, you can show that the semicircle integral of this integrand equals to 0 by Jordan's lemma, precisely because we're considering the case where t is less than t prime, and as a result the exponent is the e to the power of this thing, the coefficient of this omega is positive. So we can apply Jordan's lemma, and as a result we can show that this term is 0. So what do we have now? We have that the integral that we are interested in evaluating, the retarded propagator, is equals to the integral of this integrand, and it in turn equals to the contour integral of this integrand. So now we just need to evaluate this. But what is this? This is simply a contour integral, and because f of omega has no poles inside C, inside the upper half plane, because remember we pushed the poles down, so the poles live in the lower half plane, they live below the real axis. So if we integrate over the upper complex plane, then this integrand has no poles, so this is actually just equals to 0. So what do we know? So now we know that g of r is equal to 0 if t is less than t prime. And indeed we have completed the first half of the proof, where the case where t is less than t prime, the integrand is 0. So now for the second part, for the more interesting part, if t is greater than t prime, then t minus t prime is greater than 0. And so if we tried the same approach again, then Jordan's lemma wouldn't work anymore, because the term in the exponent is no longer positive. So instead we need to close the contour in another way. And what do? We close the contour in the lower half plane, such that this contour, this semicircle, is now 0. So we have integral over contour C, redefine the contour C, is equals to minus infinity to infinity plus this contour, this semicircle. And by Jordan's lemma again, this is simply, the semicircle is simply 0 by Jordan's lemma. By Jordan's lemma with the added assumption that with this assumption, which allows us to apply a Jordan's lemma. So we have this. So now what is our retarded propagator? Is simply the closed contour integral C of f of omega d omega. And now there's two poles that live within this contour, and because we are integrating in a clockwise direction, is minus 2 pi I times the sum of residues inside C. Okay, so how do we compute the residues? So let's first write down the form of f. Taking it from above, we have so reminder that this formula is just this over here. I'm just rewriting it so for sake of ease of reference. So what do we have? We need to calculate the residue of this function f of omega at omega equals to minus ck minus I epsilon, and this equals to e to the power of minus I. Okay, for the first one I'll write out in more detail. So it is equals to omega plus ck plus IE times f of w, the whole thing evaluated at omega equals to minus ck minus I epsilon, and this equals to e to the power of minus I minus ck minus IE t minus t prime over minus ck minus IE minus ck plus IE, and this equals to assuming that epsilon, we take it as a limit tends to 0, we have minus 2ck at the bottom, then e to the power of plus I ck t minus t prime. Okay, so that's the first residue. Now what's the second residue? Second residue is simply the same similar procedure, and I need to do e to the power of minus I omega minus plus ck minus IE t minus t prime over the bottom. The bottom would be 2ck. So this is equals to taking the limit where epsilon approaches 0, we have e to the power minus ick t minus t prime 2ck. So now we sum the two residues. We take this plus this. What do we get? We get minus 2I sine ck t minus t prime over 2ck, and this is equals to minus I over ck sine ck t minus t prime. Now we plug it back into our formula here. We multiply it by minus 2 pi I. So now we have the end result equals to minus 2 pi I minus I over ck sine ck t minus t prime equals to minus 2 pi over ck sine ck t minus t prime. And that is for the case where if t is greater than t prime. where's my working? And for the case where t is greater than t prime, and we see that we have in fact solved this integral for the two cases where t is less than t prime and t is greater than t prime. And so with that, we've come to the end of the video. I hope that this video has illustrated to you how to solve the retarded propagator in electrodynamics in the Lorentz gauge, and more importantly, how contour integrals may appear in physics in the most unexpected manners in electromagnetism. So I look forward to the next part where we talk about the Feynman propagator in quantum field theory. Have a nice day. Bye.